All right, it's 5:30, so let's go ahead and get started. Good evening, everyone. How's everyone doing today? Good. Good. Excited for Thanksgiving? That's good. That's good. Thanksgiving is the time to, normally, the reason the school thinks that they're giving everyone a break is that everyone can unwind and spend time with family. But, I think we all know that Thanksgiving is the time to catch up on work. That's kind of the unfortunate reality. And with that said, we're doing our 7th ANSYS activity. Okay, so we've done a lot of them this semester, and for me, this is uncharted territory because I've never actually done more than 6 ANSYS activities in a finite element class. But the feedback that I always get from my finite element class is that we wish that we could do more. Not more work, of course, but just learn more features in ANSYS. And so this is kind of a new thing to me. So. I know the activities are a lot, but hopefully you guys are enjoying learning all these different features. Okay, and today we're doing an important one, and so today we're learning about modal analysis and vibration analysis. And so I think this is probably one of the most requested ones that I've gotten in the past, because vibrations is a really important topic to learn. If you're doing any kind of anything that involves structures of any kind. Then testing your structure against vibrations is really important because you can make a really great structure that has a ton of factor of safety. It doesn't even come close to elastic yielding, but if it's going to resonate and if it has a poor natural frequency, then all of that's going to be for nothing. Okay, and so we're going to learn today how to actually perform this in ANSYS, right? And so there's one CAD model that you need for this activity. And so if you go to the course website, you'll see that there's a CAD model for a gearbox, okay? And it's a workbench file. And so, I should say it's a design modeler file, okay? And so you can go ahead and download that and open up Workbench. And we can go ahead and get started, okay? And I guess before we really get rolling, the due date for this is going to be the Friday after Thanksgiving. And so, next week's going to be Thanksgiving. So, nothing's going to be due during Thanksgiving, and it's going to be due the Friday after that. Okay. And so when we come back from Thanksgiving, I have one more activity planned for everyone, and so that's going to be an activity on buckling. Okay. And there's not much to buckling, and so I imagine that's going to be a pretty short activity. And then the last week, we're just going to do miscellaneous topics, and so the way I'm going to do the last week in the class is I'm going to basically tell you or put out a poll of all of the extra features in ANSYS that we didn't get that I know about that we didn't get a chance to go over in the class. And I'll let you guys vote on that last week on what you guys want to see the most. And so I have lecture notes on thermal analysis and ANSYS. I have lecture notes on fluid analysis and ANSYS. I have lecture notes on anisotropic materials and a few other topics too. And so I'll let you guys choose on what you want to see on that last week. Okay. Okay. And so with that said, are there any questions I can answer before we get started? Okay, all right, so go ahead and download the CAD file and then open up ANSYS, okay? And then where we're gonna start is with a static structural analysis, okay? And so in the workbench, just like we normally do, we're gonna drag static structural and we're gonna put it into this zone right here, okay? And then we're gonna import our geometry just like we've always done. So we're gonna right click on geometry, we're gonna go to import, and then we're gonna look for the gearbox, which I think is in my downloads. And then we're going to have that loaded there. Okay. And before we jump into mechanical, we have to add some engineering data. So let's go ahead and double click engineering data. We're going to go to engineering data sources. Okay. And we're going to go to general materials. And then we're going to add the material properties for gray cast iron and then also stainless steel. Okay. Right. And so we're going to have 3 materials overall. So we're going to have gray cast iron, stainless steel, and structural steel, okay? And all of these you can find within the general materials. And so, you go to general materials, you click on engineering data sources up here, and then you click on general materials, and then you're gonna click on the plus buttons next to gray cast iron and stainless steel, okay? And so if you do all of that, and you go back to your material list, you'll have these three materials, okay? So is everyone able to get these materials loaded in ANSYS? Yeah, we've done this so many times now, so it's hopefully it's muscle memory for you guys. Okay, and so now that we have the materials loaded, let's go ahead and open up mechanical. So let's go ahead and double click model, and then we'll get started with that.
So would you say gray cast iron and stainless steel?
Yes. Yeah. Mm-hmm. So taking a little bit longer to load than usual. Okay. All right. And so once your geometry loads up, then you should be able to see it just like this. Okay. And the geometry that we're considering this week is a gearbox. Okay. And so it's a little bit of a simplified version of a gearbox, just so that we can mesh this easily. But what you can imagine is that on the inside of this housing here are a bunch of gears. And so you would find one of these inside the drivetrain in your car. Or any kind of machine where you need to apply some kind of gearing ratio. Okay, so either to gear up or gear down. Okay. All right, and so if you click on geometry here, you can see we have 3 parts to our assembly. And so we have the housing, okay, which is the kind of the shell part right here. We have the flange, and so this is where shafts are going to insert. Okay, and so normally you can imagine a shaft is inserted here, and on the inside it connects to a gear. Okay. And then we have the base, which is the bottom part where we're going to fix it. Okay. And so if you'll notice, there's a question mark next to the housing right here. Okay. And so remember, a question mark in ANSYS tells us that we have to specify something here before we can move forward. Okay. And if you go to the bottom left of the screen, you can see that the parameter that's missing here is the thickness. Okay. And so thickness, that seems kind of strange. Why would we need to supply that? And so to kind of see why we need to supply thickness, you can go ahead and hide the base, okay? So you don't have to do this. So I'm just doing this to show you, okay? And so you can see from this image here that the housing is a shell, okay? And so it's a very thin, it's a very thin surface. And so it was, something that the previous person who made this CAD model said that, since this housing is very thin, I'm going to go ahead and model it as a shell. Okay. And so as we know, if you're going to work with shells, you need to supply a thickness to that shell. Okay. And the thickness that we're going to supply here is going to be 3 millimeters. Okay. And so if your units are in meters like mine, you're going to specify this as 0.003. Okay. And so that's going to be the thickness for that shell. Okay. All right, and so the next thing we have to do is we have to supply our materials. Okay. And so for the housing is going to be made of stainless steel. So let's go ahead and change the material properties from structural steel to stainless steel for the housing. And then for the flange and the base, we're going to change this to gray cast iron. Okay. Right. And so once again, for the housing, we're going to apply a material of stainless steel. For the flange, we're going to apply a material of gray cast iron. And for the base, we're going to apply a material of gray cast iron as well. Okay. All right. Any questions on this? Okay. All right. And so the next thing that we're going to have to specify is the connections between the parts. Okay. So we have three parts here, and so there should be 2 connections, right? And so there should be a connection between the housing and the flange. And there should be a connection between the housing and the base. Okay, so let's go ahead and check. Let's go and check and see if we have all those connections. Okay. And so if you expand out the connection tree in your project outline, you can see that we do have one connection region. Okay. And if you click on that contact region, you can see that the contact is between the flange and the housing. Okay. And so these 2 parts are already bonded to each other. And so these are good. Okay. But you can see that we don't have a connection between the housing and the base. Okay. And so we need to create. Okay? And the reason that we don't have a connection here is that because our housing here was a shell surface. If I can hide the base here one more time just to show you. Okay. Then when the housing comes down, you can see that it comes down to an edge because the shells are infinitesimally thin. Okay. And so whenever you have an edge like this that's being contacted onto a different surface, ANSYS doesn't generate the connection automatically for that. Okay. And so this is the same reason why when we did our bridge activity, we had to add in all of the connections on our own because all of the connections were either an edge to a surface or a point to a surface or a point to an edge. Okay. And so whenever you have an edge that's connecting on a surface, ANSYS is not going to generate that contact for you. And so you need to do it yourself. Okay, so let me go ahead and show this body again. And so let me go ahead and create another contact region. So I'm going to go right click on contacts and I'm going to do insert manual contact region. Okay. And so that's going to create a new contact between the between the 2 surfaces that we denote. Okay. And we want to connect the bottom edge of the housing to the top surface of the base. Okay. All right. And so this is a good time to test your knowledge, actually. Remember, when we talked about nonlinearities in class, a couple of weeks ago, we talked about how it's important to select these in the right order, right? Because we have to select one surface as the contact and the other surface as the target, okay? And so, I'm not going to do it right now, although I guess if you look at the PDF, you can see the answer. But, if you consider the one of the surfaces that we want to mate as the top surface of the base and the other one to be just the bottom edge of the click here to make it easier, the bottom edge of the housing, I want you to choose which one should be appropriate, right? So between these 2, between this edge and the surface of the base, which one of these should be the target? Okay, and so I'll give you guys a couple minutes just to go ahead and choose this, and then I'll follow you up in a couple minutes. Okay? Yep.
Do we just connect the one of the edge, or for the 4 edges?
It has to be all 4 edges. Yeah. Yeah, and so you have to be careful on this too. So when you're selecting the bottom edge of the housing, you have to hold control and click because you can't select all the edges at the same time. And so you have to hold control and click all 4 edges. So make sure all 4 edges are selected, when you apply it to the connection. Okay. It does matter which one is the contact and which one is the base. And so we talked about this, when we talked about nonlinearities. And so, maybe one more minute, and then I'll show you kind of which one that you should, which order that you should do it. Right. And remember, it has to do with how ANSYS checks for collisions and how it checks for penetration, basically. Okay, so did everyone make that connection? Okay, and so remember, the difference between contact and target is that when ANSYS checks, and so basically what's going to happen is that the reason we're defining a contact region between these is we want ANSYS to define how those 2 parts are going to interact. Okay, and so one important interaction that they're going to have is ANSYS needs to check and make sure that after we apply forces, that these 2 surfaces don't clip into each other, and so they don't penetrate into each other. Okay, and the way that ANSYS checks this is that it takes all the points on the contact surface, and it checks to make sure if none of those points are penetrating through the target. Okay, and so it's going to check, it's going to take the contacts and checks if it penetrates through the target. Okay, and so for that reason, the surface that you pick for the target, that should almost always be the bigger of the 2 surfaces. Okay, and so when you have one surface that's an entire face and another body here, which is an edge, you want the target to be that surface because that one just has a larger surface area. Okay, and so you can see right now that I've selected the contact to be the face and the target to be the edges. Okay, and you can see that ANSYS is complaining about this, and so it's saying that this is not good, and so we need to switch this up. Yeah. Question, Jacob?
Okay, yeah, I was asking because you said the opposite of your screen.
You made us change it. I had it.
I did this to trick you guys. So it should be the other way, but I did this on here sneakily just so that to make you think about it. Yeah. And so if you're like me and you selected them to be opposite here, you don't have to reselect everything, and so you can right click on the contact here, and you can click on flip contact and target. Okay. And so it'll flip those 2 things, and then now you should be good. Okay, so the target here should be the base, okay, which is this large surface here, and the contact will be the 4 edges of the housing. Okay.
I'm sorry, where did you write that?
Oh, you right click on the contact here, and then there's a button for flip contact and target. Yeah. Yeah. And so that's an easy way. So the nice thing is that ANSYS will tell you if it doesn't think it's correct. And so if you make a contact. And so let's say that you're doing your final project and you're doing it on a different geometry, and you try to make a contact like this. If ANSYS doesn't like it, it'll tell you, but then all you have to do is just right click and just flip it, and then that'll usually fix it just fine. Okay, all right, and so that's the contacts. And so next we have meshing. And for the mesh, we're not going to do anything special here. So I'm just going to go ahead and just do the default mesh. And so you can just go right click on mesh, and you can just generate the default mesh. Okay. Oh, I forgot. So one thing you do want to make sure that your element order is quadratic. Okay. And so when you left click mesh right here, make sure you click on quadratic order. Okay. So I forgot to do that. So let me go ahead and update my mesh with that. Okay. But in terms of the sizing, we're not going to worry about the sizing. So for this activity, it doesn't matter all too much. And so the only thing we just have to make sure is that we have a quadratic mesh. Okay. Okay. All right. And so now that we have the mesh, the next thing is we're going to apply boundary conditions. Okay. And here, I'm actually going to show you one type of boundary condition that we haven't used yet, which are bearing modes. Okay? So some of you may have already done this, and so those of you who did the shaft housing for the midterm project, you probably already used this. But I'll show you the difference between applying a force boundary condition versus a bearing load in a situation like this. Because it does make a subtle difference. Okay? But the first thing we're going to do is let's go ahead and fix this. Okay, so let's go ahead and right click on static structural and then click on fix support. Okay. And make sure you're on the right selection mode. Okay, so we're going to fix it on the very bottom of the base. Okay. Let's go ahead and select that. Okay. And then next we're going to apply bearing loads on each of the 4 holes. Okay. And so if you go to the project document, okay, the forces that we're going to apply are summarized in these 2 figures. Okay. And so you can see I've labeled each of the holes. And so if you look at the gearbox from kind of this angle right here, okay. And so if you look at it from the isometric view, the A hole is going to be the one that's in front right here. Okay. The B hole is going to be the one that's on the right in the front. The C hole is going to be on the left back, and the D hole is going to be on the back right. I realized what I said, but it was already too late, and so I said A hole, and I was just going to roll with it. Okay, and so for the for hole A, you can see here that we have an F direction force of 16,000 newtons, a Y direction force of 30,000 newtons, and a Z direction force of 16,000. Okay. And so let me go ahead and apply that, just using a force constraint first, okay? And I'll show you the difference between a force and a bearing load, okay? All right, so I'm gonna go ahead and select surface A right here, okay? And we're gonna define it by components, just like we usually do, okay? And so the force and the X component is gonna be 16,000. The force in the Y component is 30,000. Okay. And the Z component is going to be 16,000. Okay. Okay. So actually, let me do this. Okay. All right. And so when we apply a force constraint like this, it's a little bit hard to see because my mesh is on top. Actually, let me turn off the mesh so we can see. There we go. Okay. And so when we apply a force boundary condition like this, and so we've done this, dozens of times in this class, right? And what I've told you before is that, when you apply a force on a surface like this, it applies the force evenly distributed across the entire surface, right? And so what that means is that, we're applying the force in such a way that this force is very evenly distributed. Which is great for a lot of options. Okay? And so for a lot of situations, this is exactly what you want. So if you have like a wind force that's applying a force onto a building, you want that wind force to be kind of distributed evenly all throughout. Okay. But for a situation like this, where this forcing is essentially due to a shaft being inserted into this hole and being pulled that way, that may not be exactly what we want. Okay. Because if you can imagine, if you inserted a shaft onto this hole right here, okay. So let me go ahead and draw that in. Okay. And this shaft was being pulled upwards like this, right? Then we know the hole here is going to be subjected to a certain amount of force, right? But that force is not going to be evenly distributed throughout the entire hole, right? And so if we look at kind of a view like from here, okay, right, and we're applying our force in that direction, right? Because the shaft is being pushed into kind of this upper part of the hole right here. And let me use red actually. Okay? Because the shaft is being pushed into this upper portion of the hole, what we expect is that this portion of the hole should be experiencing higher loads or higher forces than the other side. Okay, and so on the other side, the shaft is being pulled away from that hole. Okay, and so we shouldn't expect to see a lot of forces on that side. And if we use a regular force boundary condition in this case, then we're kind of ignoring that fact. Okay, because the regular force boundary condition says that okay, we have this entire surface right here. Okay, let's apply this force evenly on all parts of the surface. Right? But for a bearing like this, that's not necessarily the case. And so if you look at the figure that I have in the problem in the specifications, what you'll see is that the bearing load takes this into account, right? And so bearing load will automatically kind of do this almost like an elliptical shape, where most of the force is going to be concentrated on one side, which is the side in which the shaft is impinging on the hole. Okay. Whereas the other side will not have any force at all. Okay. And so for situations like this, where you have a bearing and a shaft inside the bearing, using a bearing load will be a little bit more accurate to simulate your forces. Okay. And so let's go ahead and do that. Okay. And so let me go ahead and, and we're still going to use this. And so let me go ahead and suppress this for now. Okay. And instead, let's go ahead and insert a bearing load. Okay. And so you can see the bearing load looks like this. Okay. And so it almost looks like a very flamboyant diamond ring, I guess. Okay. Okay. And so let's go ahead and apply this bearing load on this surface. Okay. And we can rename this too, just because we're going to apply a lot of forces here, and so we'll call this bearing load A, just to make sure that we know we're on the surface A. Okay. And then let's go ahead and specify the components for this force. Okay. All right. And so for the components, you can see if we go back to the document, we have 16,000 for the X component of the force. Okay. We have 30,000 for the Y component. And in the Z component, we have 16,000 as well. Okay. All right. And so, that's what you would apply if you can apply this force. Okay. The problem with this is that, the Z component in this case, you can see the Z component is pointing axially down through the hole, right? And so the Z component force is what we call like an axial force. And the thing with bearing loads, and one weakness of the bearing loads is that you cannot apply an axial load, with the bearing load like this. Okay, and so if you try to run this right now, ANSYS will actually give you an error because it said, I detect an axial load in this bearing, and I can't do that. Okay, and so in order to make this run, you have to set the Z component of the bearing load to 0. Okay, and then for the force that hopefully you didn't delete, hopefully you still have it. Okay, this is where we're going to supply the axial load. Okay, and so for the regular force boundary condition, you should have 0, 0 for the X and Y component, and the Z component should be a positive 16,000. Okay, and so we need to apply both of these force boundary conditions in order to supply the full loading on this hole. Okay, and the main reason, remember, is because the bearing load cannot support any kind of axial loads through the bearing. Okay. All right. Any questions? Any questions on how we set this up? Yeah.
You're saying you're adding another force because it is acting in the axial direction of the axis of the bearing.
Yes, exactly. Yeah.
And why can't that work as a bearing load?
Because the bearing load, ANSYS is going to assume that it's going to make a force profile that looks like this. And so if you have an axial load, then this kind of violates that property because it assumes basically the load is being placed perpendicular to the surface of the hole. And so if you kind of add an axial component that kind of shifts it, into the hole or out of the hole. And so you need to kind of remove that. Yeah.
Is the bearing load essentially only applying compressive forces from the shaft?
Exactly. Yeah, that's exactly what it's doing. Yeah. Mm-hmm. Yeah. And so because the bearing load can only do compressive forces, then an axial force doesn't make sense because an axial force has no way of compressing against the sides of the bearing. Okay. All right, so let me go ahead and relabel this. Okay, so I'll call this force A. Actually, I'll call this axial force A. Okay. And so and so the magnitudes and directions of all the other forces are given in the document. Okay. And so it's on page 6, I believe. Okay. And so why don't you guys go ahead and fill in the rest of the loads, and then I'll catch up with you afterwards. Okay. Yeah.
That little arrow. This looks slightly different.
It should be.
Yeah, it's 16. Yours just looked defined. Yours looked defined from the inside.
Oh yeah, it shouldn't matter. I think it's just a rendering. So I think it places the arrow just kind of wherever it wants to put it. Yeah, I think it's
We have to add a separate axial force to each bearing load, right?
So there's only two axial loads. I think it's on bearing A and bearing B, but B and C don't have an axial.
Oh,
Yeah, so you should have 6 loads altogether, 4 bearing loads and 2 regular axial.
You have to solve an actual
All right, so was everyone able to apply the all the loads and the fixed support to this for the gearbox? Okay, I'm seeing some nods. I'm seeing some good. Okay, chat. Great. Okay, and so with that, let's go ahead and run the simulation. And so let's go ahead and insert a total deformation field. And let's go ahead and insert equivalent stress. Okay, and let's go ahead and run it. Hopefully it doesn't take too long, although it might take a little bit of time. This mesh isn't too bad. Okay, and you should get results that look like this. Okay, all right. And so you should get deformation fields that look like the following. Okay, and you should get a deformation of 0.000768 meters. Okay, so actually let me change these units just to make it a little bit easier to see. Okay, and then the maximum equivalent stress should be around 232 megapascal. Okay, and so this looks a little bit gnarly right here, and so it looks like our bearings are coming off the housing, but that's because our result here is being auto scaled. Okay, and so it's making the deformation look 53 times greater than it actually is. And so if you want to see true scale, you can go up to the results section of ANSYS mechanical, and then change this setting right here. Okay. And so instead of 53, which is the auto scale, you can change it to true scale, and you can see that your gearbox is just doing just fine. Okay. All right, and so that's the static structural. And so, none of that was, so all that we've done before. And so now let's kind of get on to the newer stuff, okay? But the reason we did static structural first is so that, we can set up all the boundary conditions that we need to here, that we can just import it directly into Modal, okay? So this is usually good practice for you to do, because, a lot of times it's good to kind of, make sure that your mesh is good, and your boundary conditions are good in static structural before you import that into Modal. Okay. All right, and so let's go ahead and return to Workbench. And so you don't need to close mechanical. And so I know in the document I said to close mechanical, but you don't need to. Okay. So let's go ahead and return to ANSYS Workbench, and then the analysis that we're going to add is called Modal here on the right. Okay. And so let's go ahead and click on Modal, and then we're going to drag it onto here. Okay. And so you can click it and drag it either onto Solution or onto Model. And so I'm going to go ahead and drag it onto Model. Okay. And so after doing that, you'll see that it'll make a connection between your static structural and the new modal analysis. Okay. And so if we come back to Workbench, what you'll see is that it's created a new setting for you for modal analysis. Okay. All right. Okay. And so now what we can do is we can go ahead and run this modal. But before we do that, we have to fix our gearbox. Okay. And so you can run modal analysis in I would say 2 different modes. Okay. And so you can either run it in a stress-free mode, or you can run it in a pre-stress mode. Okay. And you can change those settings here with this pre-stress setting. Okay. And so what the pre-stress is that you can run modal analysis to compute the natural frequencies in your system. You can either do that when your structure is free and it doesn't have anything loaded onto it, or you can do it when it's stressed. Okay. Because when you apply stresses onto a system, right? And so when you apply all these modes, it actually changes the overall stiffness of the structure a little bit. Okay. Because remember, when you apply loads to a structure like this, it's deforming to some certain degree. And when the structure deforms, it changes a little bit of its geometry. You're changing a little bit of how the material acts. Okay. And so all of those factors can actually change your result for the modal analysis. Okay. For now, I'm just going to say it's none. And so we're not going to import our static structural results. And so I'm just going to run it in a stress-free configuration. Okay. But in order to do that, you have to insert a fixed support. So go ahead and right-click on Modal B5 and insert a fixed support. Okay. And so we're going to fix it in the exact same location. Right. And so, basically what we're computing the natural frequencies of this gearbox, without any modes. Okay. So let's go ahead and click solve. Right. And so it's going to solve your system again. Okay. And hopefully it doesn't take too long. And so once it's done, you can go ahead and click on solution B6 right here. Okay. And then in the bottom of the screen, you'll see, 6 frequencies here. Okay. And so these are the first 6 natural frequencies of your structure. Okay. All right. And so, what this tells us is that the lowest natural frequency of our structure is 315.18 hertz. Okay. And so if we force the system at 315.18 hertz, then resonance will occur. Okay. And in fact, you can actually view the mode shapes for these as well. Okay. And so remember what we talked about on Monday, that once resonance occurs, it's going to cause the deformation to change in a certain way, right? Or that's what kind of the resonant mode looks like. And so you can view what those look like. And so if you go here and you highlight all of these frequencies, You can go ahead and right click them and then click on create mode shape results. Okay. And so you can see after you do that, it'll create 6 deformation fields, one for each of the mode shapes that you created. Okay. Right, and then we'll go ahead and solve it again just to evaluate those quantities. Okay. And if you click on any of these, you'll be able to see what the different mode shapes look like. Okay. And so if resonance is going to occur in this structure at this frequency, then the deformation field will look like this. And if you click on the play button, you can see the resonance in action. Okay. And so it's a little bit hard to see, but you can see that once resonance is occurring, then we're going to have this part of the gearbox kind of being bashed in. Okay. And the entire gearbox itself is going to be kind of swaying back and forth. Okay? And you can do the same thing for the second mode. Okay. And so for the second mode, the resonance is going to occur just on this bottom section. Okay. Right. And so if you apply an oscillating load at a frequency of 402.69 hertz, then this is what you're going to see. Okay. And for the third mode and the fourth mode and the fifth and so on. Okay. Okay. So the fifth one is kind of interesting. Yeah. Question. Yeah. So you click on solution B6, and then for these, all of these frequencies here, you're going to highlight all of them. You're going to right click, and then you're going to click on create mode shape results. Yep. Yep. All right, and so that's how you compute natural frequencies, in ANSYS. Okay. Now let's compare the results. And so I just got done saying that the results are going to change if you add the pre-stress. Okay, so let's go ahead and add that in. And so let's go to pre-stress here. And then for the pre-stress environment, you're going to click on static structural. Okay. And if you'll notice, once you click static structural, then the new fixed support that you added is going to go question mark. Okay. Because now we have basically 2 fixed supports. Because now the modal analysis is inheriting all the boundary conditions from here. Okay. And so I'm going to go ahead and suppress this, okay, so because we don't need 2 fixed supports. And then let's go ahead and run it again. And what do we get? Unknown error. Oh, I'm sorry. So if you're going to do a pre-stress, then you need to turn large deflections on. And so we need to go back to our solution A6 right here and go to analysis settings. And then you need to turn on large deflections. Sorry, I forgot about that. Okay.
We get to there, Professor?
Yeah, so you go back up to your static structural up here, okay? And you're going to go to analysis settings, and then there's a setting here for large deflections on here. Okay. All right, so let's go ahead and solve it again.
So Professor, I'm sorry, how would make it the static structural pre-stress?
Yeah, so you go to pre-stress right here, and then you click on pre-stress environment to be static structural. Yeah. Mm-hmm. Let's see, why is this giving me an error? This did not give me an error before. Sorry about this. Real-time errors. It's weird. This did not give me an error when I did this in my office 3 hours ago. Okay, so in theory, this should change the resonant frequencies that you obtain. Okay, because once you add the pre-stress in there, that changes the geometry of your structure. Okay, as to why it's giving me an error right here, have large deflections turned on. Doing that. All Let me try one more time, but in the meantime, let me go ahead and debug this issue for a little bit. Is everyone else getting that same issue where you have to turn on large deflections? Okay, let me debug that for a bit. But you can go ahead and move on to the different parts of the activity until I fix that. Yeah. Oh, yeah, large deflections turned off and you don't get that error. Yeah, that's kind of what that was my experience when I did it on my own too. But yeah, let me go ahead and try to fix this for a bit. But in the meantime, while I'm trying to figure this out, you guys can go ahead and work on the rest of the activity. Okay. And so for the rest of the activity, I want you to use the modal analysis here and explore what happens when you change different properties of your structure. Okay. And so for problem 3, I want you to change the material properties. Okay. And so I want you to change the material properties of the housing to something other than stainless steel. And so I want you to pick a material that has a lower Young's modulus and a higher one, and then you can see how that affects your natural frequencies. Okay, and so I want you to show what happens and then also comment on it. Okay. Next, I want you to change the geometry. Okay, and so this CAD model right here was produced within Design Modeler, and so you should be able to open it up in Design Modeler and change this geometry. Okay, and so I want you to make 2 different changes to the geometry. And then see how that affects your natural frequencies. Okay. And then for problem 5, what I want you to do is given what you know from problems 3 and problems 4, I want you to make changes to the design such that you get a target, you hit a target of the natural frequency. Okay. And so in the default configuration, the natural frequency was about 300 Hertz. And so I want you to change the design such that you get a natural frequency somewhere in the ballpark of around 200. So anywhere between 190 and 210 should be good. Okay. Okay. And so why don't you guys go ahead and work on that, and then I will try to see the issue for the large deflection. Right, Aaron. Okay, so you notice I clicked on modal and then click solve for it to work. Let me try that. Yes. And so if you're going to run with pre-stress, you have to suppress the fixed support. Otherwise, it's going to have basically 2 fixed supports at the same time. This is how I do it. Oh. This is for you.
get our results to work. So I'm kind of scared now that you're not working in minded, which implies I might have done wrong.
I think this is a bug with the software because when I did this in my office, a few hours ago, it worked just fine for me. So, but are there people that are still getting this unknown error issue even with the large deflections turned on?
We should it on.
You turn it off?
On.
Or you turn it on and it's okay?
Yeah.
Okay, then that's good. And so that's what should happen. And so I think there's just a bug with this issue right here. But I was working through it just in case other people were having that issue. But once you turned on large deflection, it was okay, right?
Yeah.
Is anyone still getting this unknown error thing on their?
I got a warning signal.
A warning is fine. That's the thing with software is that you can ignore all the warnings. Ignore them until they become an issue, and then you can listen to them. But if no one else is having this issue, then it's okay. I think, we've run into a couple other issues with other systems in this lab where like I think there's a computer over there that's like really slow, and then I think that over here it's there's some issues with it too. So I think it's just a bug with this installation. So
You're still having that issue.
you're still having that issue. Okay, let me see.
Just ran and or different function on.
Yeah. And then you get the same error when you type.
Yeah, I can write it. It was right here. Just talk to me. I'm still not getting
Go ahead and right click on Modal right here, and then click solve.
Oh, just kidding.
Let's check and see. So click on solution V6 right there. Okay, great. So you can see the frequencies changed a little bit. So before it was like 315, so now it's about 30.
Yeah. Okay.
Yep. So that's
So like, is that because I'm used to pressing this solve button, so next time if I
yeah. So because you click solve and I didn't see anything happening down there. So if that's happening and you have multiple systems like this, I think what it was doing is that maybe it was trying to solve this upper one, which is already solved. And so if you click solve on this one, then it should be solved.
should solve this specific.
Yeah.
Okay.
Oh, so warning signal about very long
Oh,
this time. Actually, when you for the simulation, the simulation might come to like a lot longer than you used.
I see. Even for the static structural one?
Yep.
Okay. Yeah, I think these computers are old.
So it's just about the computers being old.
Yeah, because I think what it's saying is that it's because the processors of this computer are not that good anymore. Right? And so when it's running the computations, it's really slow. And so ANSYS noticed this, and so it says that for a mesh of this size, it should only take about this long. And so because your computer is still running, then they think something is wrong. But I think this computer itself is just really slow.
Oh, it's okay.
Yeah. But yeah, I think it's I think you might have to do it on something else just because there is a lot of solutions for this one with all the different materials and geometry. So
Maybe I can just use another computer.
yeah. They just right. Thank you. You guys doing okay?
And also move on to the activity. I forget to like take the screenshots that I need to. I change everything,
Uh-huh.
and I pretty much have to go back and do it. That's happened to me many times where you're like, move on and do the rest. And then come back to it a week later. I'm like, oh my God, I haven't showed screenshots for problem.
we sure warning now.
Professor?
Yep. What's up?
Yeah, actually, I solved it, but I'm getting a thunder sign before the solution now. Hello, thunder sign. I'm worried about that. What is that?
Oh, what we're getting?
I'm getting a thunder sign.
Oh, say again.
A thunder sign, like a mark something, an yellow mark, and on the solution part.
Uh-huh.
Yeah, what is that?
Oh, you mean the deformations that you're seeing?
You like there is a yellow red mark. I'm getting that yellow mark there.
Do you want to show your
Still
screen?
deformation.
You want to share your screen so I can take a look?
Yeah. Actually, I'm not able to share.
Oh, sorry, I need to enable it. All right, go for it.
Just asking for this thing. Why I am getting these signs before the solution?
Oh, okay. Go ahead and right click modal B5. And then click on solve. Sometimes when you click the solve from the top, it'll solve only the top, it'll solve only the static structural, but you need to force it to solve the actual modal part. And so that's how you can force it to solve that part there.
Oh,
Okay.
okay.
You should be good.
Right.
Yep.
Thank you.
Mm-hmm.
Let me see your. Let me see your. Everything else. And it doesn't look like it's that cool. I mean, for the deformation. You just use the mesh deflections. Oh, so I just see the default. It's like 16. Yeah, I think probably we're getting slightly different. Because this mesh is not that, I mean, the default mesh is not that. I think what might be happening is because our mesh is getting. Let me just double check while that's running. Let me double check and see what. Just close it.
I got you.
Okay. Yeah, I think.
कुछ बोलते हैं ताकि हमने जो भी मैंने आपको कैंडी दिया था ना एगलेस वाला उसको सारे खत्म कर दिए फिक्स कब पे खत्म कर
Ashutosh, I think your mic is on. It's 16.83. That's the default mix. Yeah.
हमें चाहिए पाएगा
Yeah, so when you change the material, I'm letting you choose what material to use. But the only thing is I want you to pick one material that's less stiff than stainless steel and one material that's more stiff than stainless steel. Yeah, so polyethylene would be very less stiff. And so, that would be good for that category. Okay, yeah, if it's giving you an error, then are you doing this pre-stress or no pre-stress? if you're getting an error, try without pre-stress, because the, oh, no pre-stress, okay. Yeah, maybe pick a material that's a little bit, not so much. You can make a custom material too, so it doesn't have to be a real one. And so you can just make like custom stainless steel and then just lower the Young's modulus. So it doesn't have to be a real one in this case. Hmm?
That really derailed your class plan.
What did?
This thing not working.
Oh no, I mean that
You
was.
got it to work? Like, is the first
Oh
time?
no, I didn't get to work, but but that was the last thing I was going to show you anyway. So
Okay.
as long as it worked for you guys, that's fine.
Fair enough.
Yeah, I was going to have you work on all the other stuff individually anyway. So yeah. All right, so we have about 5 more minutes left in class, and so I did want to mention one thing, before we all head off. Okay, and so when you're viewing these deformation results in Modal, it's really tempting to look at these results and kind of take them as truth, right? And so if we look at this first deformation mode right here, for the frequency 315.68 hertz, it's tempting to look at this and say, oh, we're going to get 12.78 millimeters of deformation right here. Okay. But that's not the case, okay? Because so modal is a very special type of analysis which doesn't actually take any loads, right? And so I know that we're applying the pre-stress from before, But these aren't true deformations, okay? And so when you're looking at these deformation fields from modal, don't take them seriously, okay? And so I know here, we have a maximum deformation of 43 almost 44 millimeters, and so that's not the case, okay? And so these deformation fields that you're looking at, these are only just for visualization purposes as for what the mode actually looks like, okay? And so if you remember from the lecture on Monday, we talked about the resonant modes in a string, right? And so we talked about the first resonant mode looks like this, the second resonant mode looks like this, okay? Third one looks like this, right? And so these are just the shapes, right? But the actual magnitudes of these deformations, remember, they depend on the magnitudes of the forcing, right? And it depends on the magnitude of the sinusoidal or the oscillating forcing that you're going to apply. Okay? And so in modal analysis, we're not applying any of that forcing. And so we're just all we're checking is, what are the natural frequencies in our structure, right? And so if you actually want to see, real resonant deformations, you can't do it from modal. And so you need to use another analysis system called harmonic response, okay? And so this is the analysis type that we talked about kind of at the very end of lecture on Monday. And so what you would do is you would click and drag harmonic response onto here, okay? And then you do the analysis in harmonic response, okay? And so the thing with harmonic response is that you actually have to apply a sinusoidal loading on this, okay? And then you can view the results, okay? And so I didn't have you do that on this activity just because I thought it was kind of enough already, and it's kind of already late in the semester, and I know you're working on your final projects. But in case you were interested in doing an actual like vibration analysis, and so if you wanted to apply like an earthquake onto this gearbox, the way you would do that is through harmonic response. Okay? So remember, modal analysis only gives you the natural frequencies, and it gives you the shape of the deformation modes, but it doesn't give you the magnitudes. And so if you want to see the magnitude, you would actually have to apply forces in harmonic response, okay? And so I want to make sure I cover that, before we head out. Yeah, question?
Why does it even give you like the magnitude of the deformation? Like, why does it even do that when they're all not active?
Yeah, I also disagree that this is not a very good programming software decision, because like people are going to look at this and they say, oh, the units are millimeters here, and so that must be the deformation. But they only chose these magnitudes just to make it so that you can view the shape well enough, but they don't actually have any meaning. And so if I was the developers of ANSYS, I would remove this altogether.
Yeah, if they just gave you the natural frequencies without even having to choose a deformation for it,
Mhm.
then at least okay, I have a big amplitude changes at these frequencies.
Yeah.
But I'd have to do a different analysis to find what they're actually like.
Yeah, I also agree. It's not very
Ignore
clear.
those. I was looking at those and I was like, damn, 52 millimeters at this resonance
Mhm.
frequency is ridiculous.
It's that's why, yeah, they're not true. And so I wanted to make sure I say that before we head out, because I don't want you to take this too seriously for either for the final project or even worse to your job. Okay. And so if you wanted to find true magnitudes, you have to do harmonic response. Okay. All right. Any final questions before we wrap it up for the before Thanksgiving? All right, so hope everyone has a great Thanksgiving. Okay, so hope everyone has a restful break. Okay, and so I know final projects out there. I know you guys are working in other classes, but make sure you take some time for yourself. Okay, so physical health, mental health, always going to be the most important thing. Classes, you can always kind of deal with that later. Okay, and so I'll see you guys in 10 days. Okay, and so we have the whole Thanksgiving break, and I'll see you guys the Monday after Thanksgiving. Okay? So break, yes, break, in quotation marks. So. Thank you everyone for the activity today. Thank you guys for coming, and I'll see you after Thanksgiving.
Professor.
Yeah.
We need to do the static structure and the modal analysis before we move on to the harmonic.
You at least need to do modal analysis. Yeah. So the modal, so you need to do modal so that so ANSYS knows what the natural frequencies are. And then a harmonic response will inherit that. And then
So we drag the harmonic response to the modal analysis.
Exactly. Yeah. Yeah. So you don't need to do static structural before modal. And so if you want to just do a stress-free modal analysis, you can just do it by itself. But if you want to do it with stress as pre-stress, then you have to do static structural.
Oh,
first.
so if you not do the structural, the pre-stress will always be done.
Exactly.
And if so, the magnitudes of the definitions are like false, but can we build the scale of the real results in harmonic response by that? Because like for example, in one case, the definition are showing like all zeros all over the structure, and
Mhm.
in another case there are some magnitudes on the structure. So can we assume that if we run the harmonic response, the second case will have a larger deformation than the first case?
It depends on what direction your loading is going to come from. And so what's going to happen in harmonic response, like you have to choose the location where you're going to apply the loading and the direction of the loading. And so that's going to affect which modes actually come out the most. And so because each of these modes, you know, they're remember we talked about on Wednesday that they're you know, they're not integer multiples of each other. And so all of these resonant modes are occurring in different directions. That's why you have different mode shapes for each one as well. And so depending on which direction you apply the loading in harmonic response, you're going to see a different resonant mode.
Oh, so we cannot compare the real results of the definition by just looking.
Exactly. So that's why I said, you know, when you do modal, don't take those seriously. So you actually need to apply the actual modes in harmonic response, and so that'll tell you which resonant mode that you're actually.
Like it shows nothing more than a shape.
Exactly. It's just the shape. Yeah.
Right. Thank you.
Yeah.
So if I wanted to do an earthquake, like on the building, I do it in here.
Exactly. Yeah.
Okay.
And so for an earthquake, you know, you'd probably apply a force on the very bottom surface
Okay.
in harmonic response, and then you would have it just kind of shake back and forth. And then you can do it across a range of frequencies.
Okay.
And you can see which earthquake frequency will result in the most disruption, basically.
Okay, so I need to drag over the harmonic response
Exactly.
from the menu. and
Exactly.
then set it that way.
Yeah.
Okay. I'll probably end up bringing that into the office just in case I can't.
Oh, yeah.
Dr.
Sounds
Chang,
good.
going off of what Jake is saying, like, obviously you'd run a modal analysis first to see where your resonant frequencies are, then you can do an harmonic analysis and sweep it in that whole bandwidth. of-
Exactly.
Okay.
Yeah. So you'll see when you do harmonic response, it'll ask you what range of frequencies you want to check, and then you can set the lower bound and the upper bound. It'll sweep.
And just to
Sweep
make
all
sure
those.
you cover the lowest resonant frequency higher.
Exactly. Yeah.
Okay.
Or it's most of the time when you do harmonic response that the frequencies you sweep depends on your loading actually. And so if you know the earthquake is going to happen within this frequency bound, then you would just check within those bounds.
Okay, and does the harmonic response, does this fit back like deformations in like as an amplitude in millimeters, or does it go to like a? Because I know in like random vibration analysis that we do like a work and stuff, it spits it to us as GRMS, like a power value, right?
I think you can set it, and so I think you can either have it look for like maximum stress, or you can have it search for maximum deformation. It'll give you a spectrum plot where the y-axis is whatever you determine.
Okay.
Yeah.
This actually last week because it was still for big. So for the ones that did not get big, I didn't upload.
Yes, I'll upload everything. So handouts, and then just the ones you cover the class, will just be whichever one. Yeah. Victor, you wanted to talk about the class? Okay, let me answer first question. Yes, yeah, you can just use stress. Exactly. It depends on your point, and so it depends on what kind of oscillating mode sense. So if you're doing the building, I would say the earthquake is kind of the easy thing. Another thing you can do with the building is that, you know, I know in California we're worried about earthquakes a lot, but for other places, you know, the building might have some kind of, if you have like some kind of rotary pump that's rotating at a really high, that's actually a cause the building. Exactly. Yeah. And so actually, you can actually look at the textbook. So they actually do an example with that geometry exactly. Of like they have like a and they show you
I could have watched that myself. For me. For me.
Yeah. So the,
Did she even go over the shit?
so those are the frequencies that are, yeah. And they're recorded, that's not that they're referring to different sections. And so if you look at.
But she said she was, but she didn't.
They all look a little.
Oh, yeah, she did. Okay, when she
And so if you excite the.
She went over those equations, so we need to
And
basically.
so normally, normally you have all of your
Our matrix, our state matrix.
but in this case, because we're 3D, we can have that.
So once we build our state matrix, we basically put it in a for loop while.
Exactly.
When did you figure out you need to put it in the
When I talked.
So
to
we do,
Tuesday,
so 6 is a default. So if you go to.
Because I was like, we can't use
And
that
so
for
in
45,
theory,
right? She's like, no, it's not different.
Yeah.
So you put it through a for loop because with the difference equation,
Yeah, so
you're
you
basically just summing that bullshit up like a bunch of times.
6 is a default. So usually.
So you're doing a 0 plus 1 plus 2 order to get the next
There's
condition.
usually 4 or 5.
Yes.
Those are the ones that should want to choose. You don't have
no
the
idea how to fucking do that shit.
It's harder.
Yeah,
I was
when you
so
asked me though,
confused.
I
I
was
was so
so
confused and she was like,
Yeah. Exactly. Yeah, so I did this right first, just so that. But if you don't want to do the
and I was trying to figure out how to work it out the truth values.
Yeah.
And I just wasn't. So that's when I had to ask the arbitrary. She would like help me with that.
Okay, tell me which part of 1A you covered. 1A, you said you did the analysis.
No, it was B and C.
So 1A was fine. 1A was just.
Okay, that was fun. Yes, we were good on that.
Okay, that didn't change anything. Okay, so B was, find that.
Yeah, we used the wrong.
Okay. On 1B, inverse A minus BK.
Yeah.
I don't know what, so you have,
Right.
oh, and you
Yeah,
can do.
so
it
a lot of
all
people
step.
ask me about this too.
She got.
So, the thing is,
Basically, she was like, your code is
the
done.
fluid pressure is always back to normal.
She's like, look at your code, there's so much going on.
And so
It's so
for
hard.
height,
And I was like, okay, just tell me.
the fluid pressure is
So basically, what
And so when
happens
you
is,
select it,
right, like on the right side of how she built it, where you say it's
And so
YSS
for
over
applying it.
VSS, right, but the limit of that is going to 0. So
And
what's
so this is gonna
actually
apply,
on
and
the
so
right
the
side,
arrow's kind of misleading.
what's actually on the right side
But
is the
it's pointing
transfer
up at this point, like on this.
So the transfer function equation. Say shit
That's
about
a
this.
And
I
so
didn't say shit.
That's
You
a-
did
this is
not
how I
say
did
shit.
on the whole.
Yeah, there's a lot of things, I mean,
Yeah,
Just
but
like
like
that.
You got
that's,
a value
yeah,
for that.
there's a lot of things about.
because you would have taken the limit at 0. You would have done
Actually,
the same mistake that we did here. So you have to use the limit for a discrete time.
So a
So you have
positive,
to
a
take the
positive
limit as z
pressure
goes
is
to
the
1
first portion.
Yeah.
because it's in discrete time.
Negative pressure is the
So when you take the limit
Oh,
as z goes to
So for
1,
your case,
what you have is, so you have the transfer function equation on the right side, right? Which is z, or which is c
So
times
hydrostatic pressure,
Z-
that's kind of
zi
a specialized.
minus a plus bk, right? I believe.
So
Yeah,
hydrostatic
minus a
pressure
plus
accounts
bk
for-
inverse
And
times
so the thing is
b,
with fluids, and so
right?
you do
and then obviously there's the f there, because
That's how
we're
you
doing
get
this,
the
right?
transfer.
It's different.
Yes. So since the limit of z is
And so
going to
hydrostatic
1,
pressure lets you apply
we now have to keep that identity matrix
based
there.
on.
Because when the limit was going to 0 before, it was s times the identity matrix, so it just became 0, because the limit of s went to 0. But now it goes to 1,
You can change the direction, right?
so now
And so
instead,
basically, so you can see here
we
that
have
it's
y, so now we have 1 is equal to c times
upward, just like.
I minus
And so
a
it's just
plus
a
bk
station there.
inverse
So
times b.
For this case where the type.
I minus A minus BK.
No, I minus a plus b, because it's the
And so
transfer,
you're not gonna see
it's the
that
transfer
much
function we have on the other side. Okay. It's
The type
the, it's the equation for the transfer function.
function.
And the equation for the
Don't worry
transfer
about
function
this.
is,
Just apply your pressure
Is,
at a constant pressure.
can't see what, because you pull the negative out here, so really.
This is for
what's
something that
distributed
you
inside
want to
is minus a plus b. So now what you have is. Huge difference. What is this? So it's not just.
That's kind of
So now, what
Normally,
we have
you just want to do it.
is
You have to insert like a function equals like
ISS
so-and-so.
over VS. Both of these are have
This is
C
just
plus ones here, right? Because the limit is.
But yeah, it's not something
Because
because it's
it's.
probably.
Okay, so these can't. The limit is going
Okay.
to C. It's going to one. And the limit of C goes to one, right? So then you have this equal to C times C. Minus B inverse times